I hope you can see my screen. So,
Yeah.
okay, thank you. Thank you. Last time, as you remember, we have been discussing about various point operations and basics of digital image processing or image analysis in general. Today, we'll dive a little bit more on the analysis part of the digital image, and mainly we focus on linear filters. Okay. So in the previous class, we have been discussing about this point operation or pixel-wise operations, where effects of functions are due on the specific pixels or points. But when we say filters, filtering is a process where the process that engages or incorporates neighboring elements in addition to the pixel or the point we are targeting. So we have already discussed about 4 neighbor and 8 neighbor connectivities. So when we say filter, it's all about incorporating those 4 neighbors and 8 neighbors in order to come up with some kind of effect that is due to the aggregate impact of those all neighbors. Okay. So specifically, I will be talking about filters, what filters are, what image filters are, why do we filter. I will talk about this one. And specifically, there are 2 types of filters, linear filter and non-linear filter. This is due to the functions that's being applied. If you're applying a linear function to your image, and that if the purpose of that function is filtering, then we call it linear filter. And if you are applying nonlinear functions, we call it nonlinear filter. So in relation to linear filters, we talk about convolutional operation and the properties of linear filters, application of filters, and also we'll try to see some form of nonlinear filter. And the purpose of normalization and normalized correlation and finding patterns in image. So in our today's class, I'm specifically discuss about linear filters, and the consecutive class, in the immediate class after this one, we will discuss about edges. Okay, so from the linear filters part, we are going to talk about smoothing today, with a special emphasis to smoothing. In the next session, we are not going to talk about smoothing, but another form of filter, which is called edge detection. Okay, we call them high pass filter, low pass filter, so we can classify them likewise. So let's start by clarifying the concept behind the digital image in general. So let's assume we have or we use a gray level image. So taking the gray level image as a baseline for our definition for digital image, then we can define digital image as a 2-dimensional light intensity, like digital image in general can be defined as, or the pixels of digital image can be defined as a 2-dimensional light intensity function f of x, y, where x and y denote spatial coordinates. Then the value of f at any point is proportional to the brightness, since we are taking the gray level image. So the value of f at any point xy is proportional to the brightness of the image at that point. So this basically means, just to give you some hint, assume we have an image. Here you can see an image, for instance. And let's say this point in the image, the red point, is a single coordinate or a single cell in this matrix. So this cell or this single point in the 2D matrix is a representative of the brightness of the image at that specific point. Okay, so we express the function as f of xy. Okay, f of xy. So this is basically assuming that the image is grayscale image. So as you recall, grayscale image, the pixel values for grayscale image range from 0 to 255, right? So 255. So that's why we say every pixel in a given grayscale image, which is 2D, is the output of a function f of xy, where the coordinate xy denotes the brightness, the level of brightness of that image in that specific point. So digital image is discretized in the spatial domain. When we say spatial domain, in the xy coordinate system, we represent the digital image in the 2D image format. And also it's discretized in the brightness domain. When we say brightness, so there is another domain in addition to the spatial coordinate. Like, for instance, you can describe this f of xy, or this point, red point here in the top middle of the image, as an outcome of f of xy. So the coordinate xy represents that specific pixel in the spatial domain. But if you talk about the function f of xy, that means we are talking about the brightness of that specific point, then we say we represented the digital image or discretized it in the brightness domain. So we can describe digital image in two domains. The first one in the spatial domain, as we already said, xy is dedicated to some pixel, one pixel, which further or in turn constitutes the overall image in collection with or in cooperation with other similar pixels. And f of xy is the level of brightness of that specific coordinate, or a pixel in that specific coordinate. We call this kind of representation discretization of image in the brightness domain rather than a spatial domain. So we have seen different operations so far, but what operations can we perform on pixels? In the previous class, we have seen point operations, right? So in our today's class, we start looking at filters which are not point operations. So if you recall from our previous class, point operations are operations that impact the point or the pixel that you are targeting, okay? It could be, for instance, thresholding, okay? So when you threshold, you are focusing on a specific pixel at xy coordinate or at xy c coordinate if it is RGB image, then the operation impacts the specific point or pixel. But when we see this kind of operations, we say it has some kind of limitations. Point operations has limitations because the first one, we cannot use them if we want to reflect the impact of neighboring pixels on a specific pixel. That's one problem. So this abstains us from using pixel-wise operations or point operations for purposes like smoothing of image or sharpening of image or alike or similar tasks, which are on the other hand, the main components of computer vision or the main components of digital image analysis. So for that purpose, we said last time, filtering techniques are there that affects the value, structure, shape of the pixel based on its the existence or based on the identity of its neighboring elements and the additional components that will be exerted on the specific pixel. So there are, generally speaking, pixel-wise, we can apply different operations. The first type of operations are point operations that only affect the target pixel, considering only the current state of the pixel and some additional function. And the other one is filter. It could be high-pass filter or low-pass filter. And the impact of this kind of operations comes from the neighboring elements in addition to the point subject to alteration or change, and also it's subject to additional function, which is the same as point operation. So we have already discussed this one, but point operations perform a mapping of the pixel values, right? The mapping of pixel values without changing the size, geometry, or local structure of the image. So this means if you have a new pixel, for instance, I prime UV, it's like image I prime or a new image I. with coordinate UV, which refers back to a pixel value. Then each new pixel in a pixel value in the new image at a point or at a coordinate UV depends on the previous value IUV. Okay, for instance, if you have this thing is not fast or conducive for organizing text. For instance, assume we have 3x3 image. So assume you have some value 1 in the middle of this image. Okay, this, let's call this one I. Let's say this one is I. Okay, then here we have assume an output of some function which we call it point operation or point function, pixelized function, that is exerted on this image and produces some kind of output which we call it now I prime. Okay, I prime. Then the output or the effect of applying point operation in this specific pixel, which is at IUV, we can call this one as UV coordinate, then can only be reflected at the same position in the new image, which is here in the middle. So that's why we say each new pixel value at I prime UV depends on the previous value I UV at the same position and on a mapping function f dot. So f dot is like f UV, but it's not specific to the coordinates UV. Okay, it's very general. Like for instance, f dot, when you say f dot, it's a point operation. It can be applied to like a coordinate fu plus 1 v plus 1 or fu plus 1 v minus 1, somewhere like that. So it's not specific to coordinates, specific coordinates, but it's generic for all coordinates in a given image. So we say f dot is a pixel or a pixelwise or a point operation in general. So the effect of point operation is resembled exactly at the same position on the new image. So the effect of 1 pixel in the original image does not affect another pixel in the new image in which is located in different location or position. Okay, so it cannot change the local structure of the image or the geometry of the image. Even it doesn't change the size of the image. It simply alters the value, the pixel intensity of the new image, So we call this kind of operations, that means operations that doesn't affect or that doesn't propagate effects of one coordinate in a given image to effects to another point or another coordinate in new image. We call this kind of operations are homogeneous point operations, because if this is if a point of operation, for instance, let's say f at UV is UV, sorry for the slow writing because I'm using my mouse. So if there is a point operation f of UV applied on image I here, then the corresponding result of this function can only be reflected at I prime of UV. Okay, so for that purpose we call this operation homogeneous point operation. Okay, so the new result is dependent on the function applied on that result. So a new action is dependent on a function applied on its the action itself. So there is no heterogeneous way of implementing your point. So for that purpose we call it homogeneous point operation. So we can extend this the above equation or dependency relationship to the image. So the new image I prime UV, or a pixel at the new image UV, is dependent on the function applied on the previous image or the original image at coordinate or at a point UV. So this we call it a function which is homogeneous. So example of homogeneous point operations are, for instance, modifying image brightness or contrast. For instance, like assume, for instance, we have a function called +1, okay? +1. That means a function that simply adds 1 to the existing pixel intensity of a given UV, pixel which is located at coordinate UV. So this simply adds the brightness to the existing pixel intensity at UV. Okay, so point operation simply modifies the brightness. It might increase or decrease, and in relation to brightness, it might increase or decrease contrast. That's one of the scenarios, the use cases for point operations. The second one is, applying arbitrary intensity transformation. So you can apply, it's the same as brightness, but you might transform by applying specific point operations to each pixel in a given gradient or in a given direction, and change the pixel intensity in that area in a way creating curves or some kind of structures. The other one is posterizing image is also possible by using point operation. Global thresholding, we have seen this one in the previous class. Gamma correction, which is again related to the contrast and brightness of the image. And in general, we can also apply color transformations. Assume, for instance, we have RGB image. We have already discussed about this one, right? We have RGB. I think I better stop writing. So assume we have an RGB image, which is a true color image, or which we can consider it as a grayscale image in 3 channels. Okay, so if you apply point operation in each point of those images in those 3 channels, you can ultimately convert or transform the color of the image. You will see this one in practice. Actually, I will give you some practical manuals and exercises, so you'll see how point operations can transform colors, how they can correct gamma, how they can threshold globally and locally. Also, different image manipulation techniques like posterizing image or transforming intensity, increasing pixel-wise brightness. When we say increasing brightness, it's simply increment operation. If you have some value like n, which is the current pixel intensity of a given pixel at a coordinate UV, then increasing brightness means image I at UV +1. That's simple. Okay. Decreasing brightness means image at UV I at UV -1. So pixel intensity -1. This is basic operation. So from the previous definition of point operation, if you consider the function for point operation as f of xy, then brightness increase means f of xy +1, and brightness decrease means f of xy -1. Pretty simple calculation. That being said about homogeneous point operations in general, and after recalling what their setbacks were, we'll now start to discuss about filter or filtering techniques. So to give you some information about these setbacks of point operations, we said point operations are limited in the previous chapter, and the reason for that were one, they cannot accomplish tasks like sharpening and smoothing. So if you see the application of smoothing, sharpening, you get to understand the setback or the limitations of point operation or homogeneous point operations. So we need really functions for us to enable or to implement sharpening or smoothing or other sophisticated computer vision tasks. We need to have a function that involves the intensities in the neighborhood of each pixel. And for that purpose, we came up with a technique called filtering, which involves the intensities of a neighboring or a neighborhood of each pixel in order to come up with the current or the new value of the current pixel in operation. So we said point operations fell short for operations like sharpening and smoothing, and this is mainly due to the fact that point operations propagate their effects only to one pixel. So the original image, pixels at the original image and pixels at the new image has a one-to-one correspondence or relation. Proportionality is also the same. But when we come, that means in the coordinate or the pixel which is affected by a function which targets that pixel will create another pixel at the same coordinate in the new image. Okay? So for that purpose, we cannot use the effect of neighborhood pixels in order to affect the state of the current pixel. So for that, we said we need filtering, and filtering is a technique that involves intensities in the neighborhood of each pixel. So we can consider, filter as a function that takes parameters like the current pixel and more other pixels which are 4 neighborhood or 4 neighbor or 8 neighbors to the target pixel. So one of the things that we need to do, which we couldn't do in the pixel wise operation or point operation, is smoothing. So the smoothing simply means that decreasing the intensity differences between neighborhoods. Okay, neighborhoods. For instance, if a given pixel at 0, 0 has a pixel intensity of 200, let's say, assuming it's grayscale, and if a pixel intensity of another pixel at 0, 1 has some pixel intensity like 5, then the intensity difference between these neighborhood pixels is very high. So for some kind of image analysis and processing, this kind of heterogeneity might not help much. So for that purpose, we might have to harmonize or try to increase the proximity between pixel intensities of neighborhoods in general. So for that purpose, we came up with this technique called smoothing. So one of the techniques for smoothing an image is by averaging, simply by averaging. Okay, so the technique goes like this. Replace each pixel by the average of its neighboring pixels. Okay, assume, for instance, we are targeting this center here with red. Okay, assume this is 1 pixel. Then by using some size of two-dimensional matrix as a mask, okay, we get to convert that specific pixel by the average of its 8 neighbor pixels, including the pixel on target. What does it mean? Assume this is a pixel on target here in the middle with red. Okay, so smoothing means transforming the pixel intensity of this central red pixel, like by the average of all neighbors, considering 8 neighbors and 8 neighbor pixels in general. So in this case, assuming all those 8 neighbors and the pixel on target, then we will have 9 pixels in general. So assuming P0 is the pixel on target, okay, then the value of this P0 can be calculated by taking the pixel intensity of this P0, okay, and by taking and summing up the pixel intensity of this P0 on all its 8 neighbors and dividing it by the number of pixels engaged in the summation operation. Okay, so this is pretty simple calculation. So just to formalize, the new pixel, which is I prime UV, is dependent on the operation P0, the operation which is the summation of pixels from P0 to P8 over 9. This is simply, we call it mean filter. Mean filter. Okay, this is one of the simplest type of image filtering techniques. So considering the image at the left side is the original image, then applying mean filter to this image yields something like you see, like the image you see in the right side of the screen. We call this one mean filter. In relation to this one, we do also have another filtering technique which is as easy as mean filter. We call it median filter. So if you know a bit about statistics, that this won't be a big problem for you. So when we say median filter, it first sorts out pixels by their level of intensity. Okay, then it picks the middle pixel as the value of the pixel on target. We call it median pixel. So there are different types of filtering techniques, smoothing techniques specifically, but these two are the easiest ones that I can say. So here, the keywords from this slide should be the first one. Smoothing or any filtering operation engages neighborhoods. That's the first thing that makes it different from point operations. Okay. The second thing, there is this concept called size of neighborhood. Size of neighborhood. So in our case, for instance, here, in order to affect the pixel on target, I'm just taking only the 3x3 neighborhoods. Okay, 3x3 neighborhoods. What does it mean? By considering the point on target as I00, I am going to take all adjacent pixels around it, or I'm going to make 3x3 matrix, or I'm going to extract 3x3 matrix and compute the mean and return back the result of this mean operation to the pixel on target. So you can also take the size of this mask or neighborhoods as, let's say, 5x5, but it's recommended to make it odd. Okay, the reason for that is that you have to preserve the symmetry of the neighborhoods. Okay, so that means taking the middle pixel, you cannot take 2 pixels to the right and 1 pixel to the left. You should keep the symmetry between these objects for better operation. Okay, for better operation. But it's not just a 1 and 0 rule. So you can take whatever you want, but the purpose of this is that take the neighborhoods of pixel on target, count them, okay, count their number, and use that count as a denominator so that you will divide the sum of it by that count in order to get the mean value for all those neighborhoods, and you could use that mean value as a new value for the pixel at hand. Okay, 2 things we talk from this one. The first one is neighborhood, the size of neighborhood. The second one, the concept of filtering or smoothing, the fact that it includes neighboring pixels, and specifically to averaging purpose. For the purpose of averaging, we simply add the pixel intensities of all neighborhoods or selected neighbor pixels by their number, so that we can get a mean value and replace the new replace the pixel on target by the new mean value. We call it mean filtering or mean based smoothing. So the reason we say this filtering is smoothing is that the operation or the result that we get after applying this function is smoothed version of the original image. So if the original image had some kind of sharpness, then the smoothing operations will decrease that sharpness to some extent. So that's why we call it smoothing. So to elaborate more on the previous example, here we have in the left side of the screen, we have the original image. We call it IUV, which is I is the image in total, and UV is the coordinate that we are targeting. And this one in relation to the point operation, this operation, this filtering operation or smoothing operation is going to affect or is going to propagate the effects of this operation to the same position in the new image, which makes it similar to the point operation. But the effect that we get or the outcome that we get for the new image is really impacted by the neighborhoods rather than the pixel itself and some other additional function. Okay, so the new image, as we already said, I prime UV is dependent on the mean of its neighborhood. Okay, so further we can say we can represent this or formulate this as I prime of UV is dependent on 1/9 because we are taking 3 by 3. Okay, don't get yourself confused. This is just for example purpose. Usually, actually, we take 3 by 3 neighborhoods, but depending on the problem, you might take some larger number of neighborhood sizes. So in our case, we do have 3 by 3 pixel. So 3 times 3 is 9. So the total number of pixels that we can include in 3 by 3 neighborhood mask is 9. So, in order to average the sum of these pixels, you have to divide the sum of these pixels by 9. So that's what we are doing here. So this simply shows, the one you see here simply shows the 8th neighborhood of the pixel selected or the target pixel, including the pixel itself. Okay, so we can simply formalize that one as a summation, a cascaded summation operation. That means if you, for instance, represent this operation, like this is 2-dimensional space, so you might use programmatically 2 for loops or 2 while loops. Okay, the first loop might consider only rows and the second loop might consider columns. So you get to add all pixels in the first column and all rows sequentially and iteratively, and then the second column and all rows in the third column and all rows. So this is what it does. So this just the value of the new pixel at a new image I prime is the sum of the product of IU plus 1 comma I of U plus I comma V plus J, these 2 coordinates. So for all J and I starting from -1 to 1. The reason we say -1 up to 1 is that from -1 up to 1 we get to discover 3 constant numbers, like as an integer we get to now 1, -1, 0, and 1. So we are taking 3 by 3 image, so that's why we put the range of the summation from -1 to 1, because we are considering the pixel at UV as the center point. So we can say it's at 0, 0, then 1, -1 to the left, -1 to +1 to the right for the x direction, and -1 to the bottom and +1 to the top for the y direction is considered here in order to come up with mean filtering for a specific pixel in a given image. Are you with me, by the way?
Yes.
Okay. If you don't hesitate, okay? If you have, this is pretty simple calculation, but I know, but if my explanations get you confused, don't hesitate to ask, okay? Because we are advancing the concepts day by day, so you have to get the root of the basic concepts in order to understand the complex ones. So here we are also talking about the same type of image, the same type of smoothing. So it tries to summarize it, summarize the concept that we have been discussing about. So in general, a filter applies a function over the values of a small neighborhood of pixels to compute the result. So the size of that filter or neighborhood could be, as I already discussed, 3 by 3 or 5 by 5 or 7 by 7 or 21 by 21, or 101 by 101. It could be, but it's recommended for it to be odd. Okay, for it to be odd. The reason is that you know, we have to consider, we have to put the pixel on target to the middle of the mask, the filter. Okay, so for that purpose, if you make it, for instance, 2 by 2, where do you put the pixel on target in this mask? It's not possible. It might be somewhere in the top left, or top right, or bottom left, or bottom right. So in order to avoid this kind of biases, you have to make your mask, or your matrix, or your filter matrix, we call it mask, constructed of odd sizes, okay, like 3 by 3, 5 by 5, 7 by 7. But it's usually recommended to use squared filters, but you can also use circular, oval, or rectangular filters. For instance, in case of Gaussian filter, you might use circular, filters, or we call them isotropic type of masks will be used. We'll discuss about that one later. So as I already discussed in the beginning of this class, filters can be linear or nonlinear. This is directly proportional to the function that you are using to operate on the pixels or on the image. If you are using linear functions, the filter is going to be called linear filter. If you are using nonlinear functions, the filter will be nonlinear filter. So the other filtering technique, the first one we already saw, mean filtering technique. We use it for smoothing purpose, okay? And the purpose of smoothing itself is to make or to harmonize the pixel differences in the same image, or in the neighboring or adjacent pixels, among adjacent pixels. But when you come to the other types of pixels, filters, the most prominent one, the most usable one and sophisticated one is convolutional filters. So the term convolution from mathematics means, creating some new function from, by incorporating or by fusing two functions. So if you fuse two or more functions or multiple functions in order to come up with new function, this is called convolving or convolution in general. Okay, so images can be filtered by using a technique called convolution. So in order to apply this technique called convolution, you have to first have a convolution mask. This is a very important one. And you have to apply separate different functions to these corresponding pixels of the original image inside the mask image in order to come up with a new value for your target pixel. Okay, so here H, this H is called mask basically. So you might say, for instance, all pixels of this H, which is 3 by 3 for now, is 1/9, for instance. So in this case, the type of operation that you are going to apply as a convolution is going to be, mean filter in general. Okay, because here in the convolution process, here we have H. Just let me elaborate it to you first, and then I will correlate it with the mean filter. Okay. Here we have, for instance, a mask. We call it H. Okay, a mask for filtering or filter size. So in our case here, it's 3 by 3, for instance. And here at the bottom, we do have I. We have been referring to this image as I whenever it is the original image. So what convolution does is it multiplies, or it applies a pointwise multiplication to each of the pixels in the mask to its corresponding pixel in the original image. Okay, for instance, this with this one, and this in the middle to the right middle of the original image, and the product of this pointwise, or the result of this pointwise operation between the pixels of the mask and the pixels of the original image is aggregated in order to get the new value for the pixel on target. Okay, for instance, let's try to apply averaging or mean filter by using convolution. So to apply mean filter by using convolution, for instance, here we can simply take a 3x3 size, filter size, and put the value of each of these mask pixels 1/9. Okay, this could be 1/9. This will be set as 1/9. This again 1/9. Then for all we'll put 1/9. Then after that we can simply multiply. The multiplication is pointwise. What does it mean? The pixel at h00 will be multiplied by the pixel at I00, and then the pixel at h01 will be multiplied by the pixel at I01. Likewise, okay, for all those 9 points in the mask or in the filter mask, and for all those 9 points in the original target image, we compute the pointwise product, and the result of all these products, so it's going to be 9 results, will be further added to get the new value for your pixel. Okay, this we call it convolution operation. And whenever in each iteration, whenever you address some pixel at 00, we call that pixel a hotspot, because every operation here is targeting what? This hotspot. So for the next one you may target this one, so this will be hotspot. So to formalize this equation, so the new image I prime UV is dependent on the sum of I of u plus 1 comma v plus j, like pointwise multiplied with or produced with the same coordinate or the same pixel in the same coordinate of from the mask. So basically I prime UV is dependent on the sum of the product of the same coordinates in the original image and the same coordinates in the mask image. Okay, that's what we already covered there. So it can be further explained as I prime of UV. I prime UV is dependent on the cascaded sum of the product of the pixels in the original image and the same coordinate pixels in the mask image. So basically, this formalization represents what we have discussed so far here in the convolution. So when we say convolution, it's a process of two functions. The first one is product or multiplication, which is a type of multiplication. We call it pointwise multiplication. And the second one is addition. So you multiply each coordinate with its corresponding coordinate in the mask and add the result of these products to the new pixel value, or replace it rather than add. It's a replacement. Okay, replace it to or put it as the new value of the pixel you are targeting. So from that perspective, we have already discussed or correlated the relation between average mean filter or averaging filter and the convolution. You can perform averaging filter by using convolution. So here we have a mask with size of 3x3 for the previous example. Okay, and each value of the mask, each value of pixels in the mask is set to 1/9. Which can further be represented as 1/9 times this matrix, which is in which all pixels are 1. So this and this are equivalent or equal. So we can apply mean filter by using convolution, using this formula that we have been discussing before. So the keyword from this content is that convolution is a function, a two-function operation. The first one is pointwise multiplication, and the second one is addition. So you can implement mean filter by using convolution. So to see some of the properties of or the mathematical properties of linear convolution, let's take a 2D discrete signal. When we say 2D discrete signal, we are talking about, you know, binary image, or like images in a 2D form. So for this 2D discrete signal, convolution can be defined as the sum of the product of if every pixel in the original image with the corresponding pixel in the mask image. Okay, so just to formalize, it starts from negative infinity for all for both coordinates and ends at positive infinity. But in between this, for instance, if you are using you know, -1 up to +1 range, or if you are using 3 by 3 mask, so this will start from I and j start from -1 and ends at +1. Okay, so if you start from, for instance, a mask of 5, so -2 up to 2 will be the range. So just to simplify, convolution, what convolution does is that it produces a new image which is the product of the original image and the mask. Okay, so this we call it convolution. So we have been discussing about the property of convolution. We have already said we have already discussed or formalized the property of linear convolution. But to furthermore on, or to discuss more on the properties of these operations, the first property of it is commutativity. We represented convolution as I times h, okay, I times h. So it's commutative. That means the result that you get by multiplying I with h is equal to the result that you get after multiplying h with I. The second operation is, the second property is linearity. Linearity. This basically means that applying some kind of value, for instance, applying pointwise operation or multiplication on one of the targets, one of the parties are here, the original image and the mask. So applying, you know, some kind of unique operation, or applying some adding, or sorry, multiplying some specific value to any of those parties in this convolution operation yields the same result. That means S pointwise multiplication with I times H is equal to I times S dot H. This is basically, you know, the property of linearity, basically. So we can also refer to this one as, you know, associativity. It's also possible to refer to it, to it as associativity. So if you apply, for instance, if I add or if I multiply each pixel of I by 2, okay, by 2, and multiply it by the h, the result that I get after multiplying h separately by 2 and multiplying the result by I, then the two results will be, you know, the same. So this is linearity, the property of linearity. So just to summarize this concept, I1 plus I2 times h is equal to I1 times h plus I2 times h. This is also type of linearity, but we can also call it as separability. Okay, separability. So we can address convolution separately. What does it mean? So assume the image in the x direction and in the y direction. So convolution can be applied in 2D image generally by using, you know, 2D mask, but also you can use 1D mask and apply that 1D mask to each of the dimensions of the 2D image. For instance, 1D mask in the horizontal side, in the x side, will be applied to the x dimension of the image, and the 1D mask, another 1D mask in the y direction, can be applied to the y dimension of the image. We call this one separability. But one thing to notice is that b plus I times h is not equal to b plus I times h. So in the case of this one, there is linearity and separability, but here this is not possible. If I add, for instance, some constant value to each pixel of the original image and multiply it by the mask h, then I will have some result. And if you compare that result with the results that you get after multiplying the two images, that means one mask and the original image, and then adding that same constant, the result will be, different. The other characteristics that we have already covered there is associativity. So A times B times C, assuming all these are 2D signals, okay? So A times B times C is equal to A times B times C. So this, we call it associative property of convolution. So associative property of convolution works for multiplication, but associative property of convolution doesn't apply for a combination of addition and multiplication. So we have already discussed about separability, but to elaborate more on separability, assume we do have a set of masks, h1 up to hn, okay? We might apply different masks, okay? So the convolution between I and h is equal to the multiplication of I with all of those masks, okay? That means after applying multiplication among these masks, you can apply the result to the original image, and the result you get is equivalent to I times h. Or in case of separability, you can apply this same operation one by one. Like you can multiply I with h1, then I with h2, the result with h2, then the result with hn minus 1 and hn likewise. So we call this kind of characteristics of convolution separability. So there are cases in computer vision that you may have to apply consecutive masks to your original image, okay? So first you might have to apply mask 1, then the result you get from this operation might have to pass through another filtering by using mask 2. Here we call it h1, h2, hn. So there are this kind of cases, necessities. So for that purpose, if you apply your operation first by multiplying the masks and then applying that result to the image, that's one possible scenario. And in the other possible scenario, you can also multiply the original image with, or convolve rather than multiply. I would prefer to say convolve. If you convolve the original image with the first mask and then the result with the second mask, and then progressively like this, the result will be the same because convolution has the property of separability. So that being said about mean filter and a special and very prominent type of filtering technique called convolution. Now let's see the types of linear filters. So there are different types of filters or linear filters. The first one could be, for instance, mean filter, or we call it box filter. Okay, box filter. The second one could be, Gaussian filter. I will talk about each of this one in detail. And the other ones, there are also other types of filters. As I already said, median filter is there. There is Sobel filter, for instance. Okay, the corresponding graphical representation of these filters is stated here in the middle, and the matrix-wise or 2D-wise representation of this box is represented here. For instance, we can say we are applying box filter if we are using homogeneous values for all pixels in the mask. Okay, that we call it box filter, as you can see here, and the edge being 0, the middle of the edge or the middle of the mask being 1, we call it box filter. Convolutional filter, we call this one because it gives much emphasis to the center of the original image and the center of the mask. Okay, this is called Gaussian filter. Sorry, Gaussian filter. So I will talk about Gaussian filter, but basically this type of filter, we already said you are supposed to multiply each of this with the corresponding pixels in the original image. So if you see here, if you are putting 0 to your mask, then what you are doing is that the value of the corresponding pixel in the original image is going to be degraded, okay, or its impact is going to be reduced. If you use a filtering pixel which is large enough, then you will boost the impact of that pixel in the original, the corresponding pixel in the original image, by the factor of this pixel, okay? So the number like shows to what area of the original pixel or the original image you are giving much emphasis. So in this case, for instance, for the middle parts of the image, you are giving better emphasis relatively, and you are trying to, you know, if you are taking, for instance, this is, I guess, a 5 by 5 mask. So for this 5 by 5 mask, the meaning or the semantics behind it is like you are giving much emphasis for the middle 9 pixels, okay? Considering the pixel on target as 0, 0, which is here in the middle, and you are trying to boost the impact of the neighboring, the 8 neighbors pixels in the original image, and trying to reduce the impact of all other pixels around it, okay? This is called square filter. The other one is Gaussian filter. In the case of Gaussian filter, again, even beyond even it's beyond the square filter. What does it mean? It gives much emphasis to the pixels which are in high proximity to the pixel on target, okay? So if you see here, the current pixel on target will have high impact on the new result, and all other 4 neighbor adjacents, 4 neighbor pixels will have relatively second level impact on the new result, and the 8 neighbor pixels will have the third step in boosting or in affecting the new pixel in the new image. So the same, you can interpret or you can have the semantic meaning of each of these pixels likewise. For instance, here, if you see here, this one is a type of filter that gives high degree of boost for the pixel on target, okay? And trying to reduce all other pixels by a factor of 2. You see here in the all 4 adjacents or all 4 neighbors are -2, and the remaining 8 neighbors in the diagonal side are -1. So this filter basically boosts the pixel on target and reduces the impact of the pixels in the 4 neighborhood, and relatively also reduces the impact of pixels in the 8 neighborhood, okay, by a factor of -2 and -1 respectively. So you could also create your own custom filter types, by the way. So the impact of these filtering techniques, we will see them in in the manual, in the lab, so that you can easily understand the the application behind the mathematics. So we already discussed about averaging, mean filter, and I have also tried to give you some insight about the Gaussian filter. I haven't yet discussed or elaborated it well, but you have some concept of what Gaussian filter is. But if you see pictorially, if you see the effect of mean filter and Gaussian filter, you can understand what the purpose of these filters is. For instance, if you see into the left side, it's a mean filter or averaging. That means if you are taking 3 by 3 pixels, this all pixels in the left side are the result of applying a 3 by 3 mean filter to the original image. But when you come to the right side of this screen, which shows how a Gaussian filter creates. So the degree of smoothness is large in the Gaussian side, and the degree of smoothness in the mean filter side is relatively smaller. So again, Gaussian filter can be made or can be configured to work like a mean filter by modifying the value of standard deviation, which is the principal component of the Gaussian equation. Okay, we'll see that one in detail, but just to have the picture of what Gaussian and what averaging or mean filter is, these pictures are sufficient. So to the left, we have averaging based resulting image. To the right, we have Gaussian based resulting image. So now let's dive into smoothing with Gaussian. Okay. So when we see the smoothing with an average or mean filter, it actually doesn't like compare well with the Gaussian filter, or it compares the Gaussian filter as a defocused lens. Okay, a defocused lens. If you see here, the result you get here is more to a defocused lens, right? So it's very blurred. So we also call this one a Gaussian blur. Okay, Gaussian blur. So you cannot compare the result of averaging or mean filter with Gaussian filter. So that's one thing. So the most obvious difference is that a single point of light viewed in a defocused lens looks like a fuzzy blob, but the averaging process would give a little square. This is reflected here, for instance. So the averaging process provides you with this kind of 3x3 square at the end of the operation, but the filtering operation by the Gaussian basically gives you something that looks like a fuzzy blob. This fuzzy blob is called isotropic Gaussian blob, isotropic blob. So something is isotropic if it is, if its symmetry in all directions is preserved. Okay, so we call it isotropic. So the thing that the filtering effect that you have with Gaussian filter is something similar to a fuzzy blob or defocused, the result of a blob being seen or perceived by a defocused lens. So it's more to isotropic. So Gaussian gives a good model of a fuzzy blob. So a fuzzy blob is a blob which looks like this one, okay? Which looks like this one. So if you see here, the point to the middle of this blob is brighter than the point to the edge of this blob, okay? That's why we said in the previous class, the Gaussian filter gives much emphasis to the middle of the or much emphasis to the pixel on target, right? So this we call it an isotropic Gaussian in general. Okay, so we have been discussing about masks, different masks corresponding to different filtering techniques here. So for instance, mean filter has something squared structure, as you can see here, but Gaussian filter has some isotropic form, okay, isotropic blob form, as you can see here. It gives much emphasis in the middle, or it has more value in the middle, in the center of the mask, and it gives less emphasis to the edge of the image, as you can see from this graph, okay? So this can be reflected here too. So let's get back to the formalization of the Gaussian blur. So graphically, in 3D form, you can represent the impact of the Gaussian filter in this graph. Okay, it has much emphasis in the middle and less emphasis at the edges. And this this matrix directly imitates or resembles the graph that you see here, which is representative of the Gaussian filter. So the Gaussian filter, the mask for the Gaussian filter is an isotropic one. An isotropic, or the best way to represent the mask of the Gaussian filter is a fuzzy blob. But mathematically, the fuzzy blob is represented as an exponentiated negative value of x squared plus y squared over 2 times standard deviation squared. Okay, so previously I already said the Gaussian filter, the principal component for Gaussian filter is the standard deviation. Okay, from the statistics class you should be able to know what standard deviation is. So the result of this exponentiated equation, x squared plus y squared over 2 raised to 2 times standard deviation raised to 2 times minus 1 gives some kind of matrix which gives more to, you know, a fuzzy blob, as you can see here in the left side. Okay, so it's circular blob and it's symmetric one. Symmetric, what does it mean? The value you get around here is more or less the same as the value you get around here. The value you get at the top here should be the same as the value you get at the bottom here. Okay, the same is true for each adjacent pixels in the mirror of 1 pixel. Okay, in the mirror of 1 pixel. So for that purpose we call it an isotropic Gaussian filter, because it uses an isotropic blob or a symmetric blob, a fuzzy blob. So researchers also correlate the mask of the Gaussian filter with you know, a defocused lens, or the view that you get by using a defocused lens and a target being the blob. So discussing more on the Gaussian smoothing technique or Gaussian filtering technique. Here assume we do have the original image. Here we have a squared filtering. So the squared filtering is mean filtering usually, so it gives this kind of resulting image. And here from the image that you can say this is a Gaussian filter, because the mask is the result of this exponentiated equation. That means the mask is more like circularly symmetric fuzzy blob, and the result is a more blurred, a more smoothed image. Okay, so here I want you to know some relationship between this. For instance, if you increase the standard deviation here, I'm sorry, I couldn't write, by the way. If it would have been great if I could write. So here we do have standard deviation. So the more you increase the standard deviation, this is just a given value. Okay, you can give whatever you want as a standard deviation, but it should be by, you know, using some empirical experiences. So if you increase the standard deviation to construct the mask of your Gaussian mask, the mask of your Gaussian filter, then the more you increase this, the more the Gaussian blurs or smooths the image. Okay, so you should be able to tune the standard deviation as a parameter to increase the degree of smoothness and or decrease the degree of smoothness of the resulting image. So the larger the standard deviation, the more it smooths the image. So in some context, if you make the standard deviation very large enough, you know, it might make the image invisible, like invisible in a sense, unrecognizable to some extent. So it's better to know the correlation or the relation between standard deviation and the overall effect of smoothing by the Gaussian blur. So we'll see this one in detail practically anyway. So the advantages of Gaussian filtering. The first thing, we are using rotationally symmetric mask. So you know, it's applicable for large filters, and it's really good not to lose the identity of the pixel on target. Okay, because here, for instance, all the 4 neighbor adjacents here in the square filtering technique, all the 4 neighborhoods or all the 8 neighborhoods will have the same impact on the pixel on target, right? But when you come to the Gaussian filter, the pixels that has high impact on the pixel we are targeting is the pixel itself, the pixel we are targeting itself. Okay, and all those neighboring pixels will have some degraded level of impact. So this is really very applicable and very practical. So that's one of the advantage of this Gaussian filter. So we already said this one, but filter weights decrease monotonically from central peak, giving most weight to central pixels. So this is also the most important aspect of Gaussian smoothing, because the image will not lose its identity. Okay, that's really very good. The other one is there is this simple and intuitive relationship between size of standard deviation and the smoothing. I have already discussed this one. The more you add the standard deviation, the more it will smooth. So as a hyperparameter, you could use the value of the standard deviation. Okay. And the other important thing regarding Gaussian filter or smoothing is that Gaussian is separable. So we already discussed about the separability characteristics of filtering. So here we discussed the separability characteristics. Here also we discussed about, I guess, the separability. Here, for instance, in this one here, we discussed about separability, like I1 plus I2 times H is equal to I1 times H plus I2 times H. So you can apply the filter separately, right? So the same is true for Gaussian filter. It's separable. What does it mean? You can apply the mask, like the isotropic mask, in the x direction for the image in the x dimension, and you can take the isotropic blob's y dimension to filter the image, the original image in the y dimension. Okay, so separately you can operate, or you can also apply a 2D mask of Gaussian blur, which is defocus, which is a blob seen by a defocused lens. You can also apply it as a 2D mask, but separately you can also apply it. So technically, like, you can formalize this separability in this manner. So we already said the Gaussian blur, or the mask of the Gaussian filter, is exponentiated form of the equation x squared plus y squared over 2 times standard deviation square times minus 1. So you can simply calculate or separate this in terms of x and y. So the Gaussian blur in the x direction is like the exponentiated form of x squared over 2 times standard deviation square times minus 1. And the Gaussian filter in the y dimension is like y square over 2 times standard deviation square times minus 1. So it's separable. So you can compute this, like in the x, you can apply the isotropic blob in the x dimension, and again separately you can apply the isotropic blob in the y dimension here, and multiply the result to get what you get when applying a 2D isotropic blob type of mask, which is a Gaussian mask in general. So the advantage of separability, I have already discussed this one, but to give much emphasis to it, it lets you first convolve the image with one-dimensional horizontal filter. It could be X, for instance. Then it again lets you to filter or convolve the image with another dimension. We can call it Y dimension. And the result can be convolved back to get the results that you get by directly applying a 2D convolution or a Gaussian convolution mask. So for a k times k Gaussian filter, 2D convolution requires k-square operations per pixel. So it's we can say the complexity of this operation is O(n) square. Okay, O(n) square. So in order to operate or convolve a 2D signal by using a k by k Gaussian filter, then you need to operate k-square times per pixel. That's per pixel. So, but using the separable filters, like using or applying the filter per dimension separately, lets you reduce this to 2 times k operations per pixel. Okay, this is a very important aspect of separability. So that's I think all about the filtering techniques for smoothing purpose. We haven't seen filtering techniques, especially linear filtering techniques for edge detection. Okay, I will be sending you this maybe in an hour, because I'm going to talk about that right after the conclusion of this session. Then I'll send you about this is an extension of this chapter, so it won't be hard for you to understand if you understand what I have already discussed in this chapter. Then after discussing linear filters for smoothing, and then we'll discuss about linear filter for edge detection. We'll talk about nonlinear filters. Then you will have a very good understanding of techniques that are applied to smooth images and detect edge in general. So I think you are welcome to ask questions. We can elaborate more on the techniques and the concept behind it, using questions. So you're welcome if you have questions.